What's up, AB Calculus students? Mr. Ford here with a homework tutorial. This one is for 4.4.1, our last section of Chapter 4, our first adventure into this little chunk there. It's all review problems. None of the new stuff from today is on here, but we are going to do all these problems, and this one might be a little long, so I might have to split it into two videos, but we'll find out. We're going to start with 4.134. We're going to split, we're going to determine the value of the following integrals, and we're going to consider all the tools available for evaluating them and use the best strategy. So these are all definite integrals, and all of them are going to be solved by, we're going to do them all by pencil and paper. Although you could, nothing stops you from using your calculator for all these problems, and I wouldn't be mad at you if you did that either. So but I'm going to show you how you could do it without a calculator, at least set it up. For question A, the first thing I'm going to do is I'm going to keep the integral the same from -5 to -2, but I'm going to just divide that m all the way out. It's going to make it 3m to the second power plus 2m minus 9 dm, which means our antiderivative is going to be m to the third plus m squared minus 9m, and we're going to evaluate that integral from -2 to -5. So what we need to do now is plug in the numbers -2 to the third power plus -2 to the second power minus 9 times -2, and we're going to subtract from that. Let me zoom in on this part a little bit because it's going to get a little hairy. -5 to the third power plus -5 squared minus 9 times -5. There's a lot of negatives involved here, a lot of stuff. At this stage, I'm just going to go to the calculator for this one. Yeah, that's what I'm going to do. I got -2 to the third. Plus -2 squared minus 9 times -2. That's the first number, 14. And then we've got -5 to the third power plus -5 squared minus 9 times -5. And that's going to be 55. And these work their way out to be 69. Nice. Okay, question B. This one I'm going to do right here in this little space. It's not going to be as long as the previous problem. The first thing we should do, though, is we should write this as the integral from -1 to 2 of 2t squared plus 3t dt. We should distribute that t all the way through. And then, again, we can find a pretty relatively simple antiderivative. It will be t to the third power, and 2/3 will go in front. That way the 3's will cancel out when we take the derivative, plus t to the second power, and then we'll put 3/2 in front. That way the 2's will cancel out, and we're going to evaluate this from 2 to -1. I wish I had made some space off to the side there. So anyway, again, we're going to let the calculator handle the most of the bulk of this work, but we're going to plug 3 in to our little antiderivative function, and then we're going to subtract from that what happens when we plug in -1. Again, I want you to practice this writing more than everything see it, because it's a pretty simple strategy. All that's happening there is we're plugging in a 2. It's a lot of writing, but it's really relatively simple. On the calculator, I'm going to very carefully work this out. I'll make my calculator cam nice and big so you can see what I'm going to do here. I'm going to have 2/3 times 2 to the third power plus fraction 3/2 times 2 squared. That's our first big chunk of this problem. Minus open parentheses fraction 2/3 in parentheses -1 to the third power. Oh, I wrote it down wrong. I'll fix it on there. Third power. Plus fraction 3/2 times -1 to the second power. Close that fraction. I think that's going to look pretty nice. That's exactly what we want to do. And it's going to give us 21/2, which is the correct answer, according to the answer guide I have in front of me, too. So 21/2, or 10.5, is what we're looking for the solution to that one. Pretty cool. Now, in the interest of time, I'm going to show you how you could do C without a calculator, and then we're going to do C with the calculator, because I feel like it's worth practicing those processes for at least one of these questions. This is going to turn really quick into the integral from -4 to -1. We should expand this out. What's going to happen is you're going to get a 1 times 1, Because remember, what you have here is 1 plus 1 over x times 1 plus 1 over x. The two 1 over x's, they're going to multiply out. You're going to get 1 with these two and 1 with these two. That's just going to be 2 over x. 1 over x plus 1 over x is going to be 2 over x. Or maybe it'd be better if we wrote this as 2x to the negative first power. And then finally, 1 over x times 1 over x is 1 over x squared. So that would be x to the negative second power, like that. And that's all dx. Now that's all well and good. At this point, you could do the antiderivative and plug in your -1, -4. But let's remember how to do this on the calculator. I'm just going to do the original integral right here. Alpha f2, find the integral. We're going to go from -4 to -1. We'll do 1 plus fraction 1 over x dx. And that's all we really got to type in. It's going to be a decimal anyway, so I'm not really concerned about that answer. That answer, oh, I forgot the squared. I'm like, that's different than what the answer guide says. It's got a squared out here. Fraction squared. That's kind of what I want there. Making sure it's going to type in correctly. That's what I want. Yes, that's exactly what I want. There we go. That's the decimal I'm looking for. It's about 0.977. That would be appropriate for AP Calc since we only need 3 decimals beyond the decimal point if you want to keep going for 1, 2, whatever. Actually, it'd be 3 if you rounded it up. And then question D, we cannot use a calculator for because we don't know what A and B are, but we'll just take a general antiderivative for this problem. The antiderivative there would be, well, I need this to be x squared, and then I'll put a over 2 in front, like that. That way the 2's will cancel out, leaving the ax. And then we'll put plus bx. And we're going to evaluate this from 3 to 2. So if we plug this in, what we're going to have is we're going to have a times 3 squared over 2 plus b times 3 minus a times 2 squared over 2 plus, I guess I'll say 2b, like that. And we're just going to shake this out algebraically and hope that it makes... Oh, hello, my face. Come on, go back. Okay. So we're going to have, in the first set of parentheses, we're going to have 9 over 2 times a plus 3b. And in the second set of parentheses, those 2's are actually going to cancel out. We're just going to have a over 2 plus 2b. So when we do our subtraction, the 9a over 2 minus 1a over 2 is going to be just 8a over 2, or 4a. And then 3b minus 2b will be just 1b, so 4a plus b is the answer there. Pretty groovy. Okay, cool. Next problem. That one took a good amount of time. Don't worry about it. They're going to move a little faster now. 3.155, the area under the graph of a function from 0 to x can be calculated using that function. Let's stop and analyze that sentence for a minute. The area under the graph of a function from 0 to x. The translation here for this question, I'm going to block off this work. That's the integral from 0 to x. The area under the curve of some function can be calculated. We don't know what the function is, by the way, of f of t dt. But we know that can be evaluated by using this antiderivative, and I know it's an antiderivative because of the capital F that's right there, of 3 times x minus 4 to the third plus 6. So here's the thinking on this problem. Since this is the antiderivative... Oops, I needed a highlighter, please. Undo. No! Ah, jeez. Minus plus 6. There we go. Oh, now it's a highlighter. Oh, gee. Blah, 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 blah. Okay. Since that is the antiderivative, f of t is just going to be the derivative of that. So here's the thinking. F of t is equal to capital F prime of t, which would be 9 times x minus 4 squared. And that would be it. The 6 would go away. So that's the function. As far as how this is the example of the fundamental theorem of calculus, it's exploring how the derivative of an antiderivative, it's actually right here. The original function is the antiderivative's derivative. So integrals and derivatives are opposites. We have one of these horizontal flag problems here with 136. We're going to take that thing and we're going to rotate it around that flag there. What's going to happen here if you do that, you're just going to have kind of like you play with a Kinder Joy egg or like a chocolate shell thing. That's kind of what you're going to have. You're going to have a sphere within a sphere. like that. It's kind of like a candy shell. So you're going to have a sphere inside of a sphere. That's what it's going to look like. As far as describing it goes, it's going to be a hollow sphere. As far as the volume for a sphere goes, I'm going to Google it really quick to make sure I don't mess it up. Because who knows? Volume of a sphere is, I'm pretty sure it's 4/3 pi r cubed. I am correct. Hey, okay. Volume of a sphere is 4/3 pi r cubed. You will be given formulas like that on your AP test. You're not expected to memorize them. But we have two spheres, so we're going to take the bigger sphere and we're going to subtract the smaller sphere. So our volume is going to be 4/3 pi times the outer sphere is 4 cubed minus 4/3 pi times the inner sphere cubed, like that. Honestly, you could probably leave it like that, and I'd be a happy guy. I know certainly the AP graders would be happy people, but let's actually shake it out. It's not going to be too terrible. 4 to the third power is 64. I got to consult calculator cam here really quick. And that times 4 is going to be 256. So we got 256 pi over 3 minus 4 times 9 is going to be... All right, sorry, brain fart. 36 pi over 3. I think that's right. And then if I do 256 minus 36, I get 220. And that's not what the answer guy says. Where did I go wrong here? 3 to the third power. Oh, 3 to the third power is 80. 20. Oh, that's the wrong number. Sorry. 3 to the third power is 27. 27 times 4. That's what it is. 108. 108 pi. That's what I'm looking for. So 256 minus 108 is going to give us 148, and that's the answer. 148 pi over 3, and we'll call it a day after that. Pretty cool. Okay, next question. 137. We're going to graph y equals g of x given below and determine if it's differentiable. The best way to graph this, I'm going to do it on a calculator. I'm just going to graph both of those functions, and we'll graph them both on the same window. We should consider the fact that we're looking at what's happening when x is 2, though. There are ways to do this analytically, but in the interest of time for this problem, we're just going to do it graphically for now. We'll come back to that later. X minus 1 squared, and then we have 2 sine x minus 2 plus 1, like that. As far as the window goes, we're concerned with what's happening when x is equal to 2. So let's just look about right around there. We'll go from like -2 to 4 for this graph, and then we'll go from -10 to 10. That should show us what's happening. If we graph this, remember the concern is the split that happens at 2. So if you look what's happening right there, this is going to be differentiable because look at the smoothness of the meeting of the two curves right there. There's no sharp corner. There's no jump. They actually have the exact same slope line at that exact point. So these are totally differentiable. And that's kind of what that looks like graphically. So yes, they are differentiable. Another way to determine if they're differentiable would be to take the derivatives. G prime of x would be 2 times x minus 1 for values of x that are less than 2. And it would be 2 times the cosine of x minus 2 for values of x that are greater than or equal to 2. And what you could do at this point is you could just plug in 2. 2 times 2 minus 1 is in fact equal to 2 times the cosine of 2 minus 2. You just plug in 2 for both those answers, right, for x, there and there. What you end up with is you get 2 times 1 over here, which is 2. And over here you get, again, cosine of 0 is equal to 1, so it's 2 over here. So the derivatives have continuity, you might say, and so that's another reason why they're differentiable. Let's look at 4.138, which is going to be kind of an advanced question. So we'll take a look at it. I don't expect you to get this right away, but I'll show you how to get the answer, how a reasonable person could figure out the answer anyway. What we're given here is we have a log falling in a waterfall, and we're given its velocity function, given by that right there. And the position of the log, in other words, where it was in time at t equals 0, is 500 feet above sea level. So it's at 500 at t equals 0. And we're asked to figure out where the graph is, or where the log is at 1 second, 2 seconds, and 3 seconds. So in order to think about this question, what you really have to realize is what you're doing is you're taking the original 500, and you're going to add on the change from 0 to 1 of that velocity function, negative 32t minus 18 dt. Because the accumulated velocity is going to tell you the change in position. The integral of velocity tells you the change in position. Now, that's not an especially difficult integral to evaluate. However, I'm going to use the calculator to muscle through it because I don't want this to take forever. We'll get the actual formula at the end anyway. So what I'm going to write is 500 plus the integral from 0 to 1 of negative 32x minus 18 dx. And that's going to tell us 466, which kind of makes sense. Basically, over that first second, we lost 34 feet of height. This thing is falling, so it's 466. Now, for the next answers, I'll write out the integrals, but we're basically going to do the same problem. We're just going to change out the number 1 to the number 2. And then, again, we'll go from 0 to 3 of negative 32t minus 18 dt. And we can do this really cleverly on the calculator by just arrowing up and selecting that whole block, and then going on here and changing this to the number 2. And then doing the same thing, and going over here and changing that number to the number 3, like that. Again, I know this is kind of an advanced question, so I don't want you to feel too discouraged. In fact, I hope you're just watching this video and you're seeing that answer for the first time. This is the first time we're really investigating the idea of how we can use an integral to figure out where something is in time at an exact moment. This is very much a preview question. So that's where it is. 466, 400, and 302 feet. As far as question B goes, they're going to ask us for an actual formula. And, I mean, I think the best formula here is the original position plus the integral from 0 to t seconds of your velocity function, negative 32t minus 18 dt. Now, of course, you could actually evaluate this integral. It's not hard to find the antiderivative of that thing. And so what you could get is 500 plus, let's see, that would have to become t to the second power. It would be negative 16t squared minus 18t. That would do it. Since you're always evaluating this integral with the bottom number being 0, it will never matter when you do the antiderivative. But that would be a general way to think about it. I strongly prefer, by the way, for you, the answer on the left. The published answer in CPM's book is this answer over here, but I really like this answer way more because I feel like it shows you the mechanics of what's actually happening there. In the interest of time, I'm going to skip 139. I feel like that's an easy problem, but I don't really care about it right now in this particular video. So what I might do is I'll do that at the end. I'll come back to it. I'm not going to assign it the more I think about it. 140 is a really good problem because 140 is going to tell you if what we're eventually going to call the product rule works or not. This is asking you if the derivative of this multiplication problem is just the derivative of the first multiplication times the derivative of the second. I'm going to go ahead and spoil the answer, and the answer is no. It does not work. And let's prove it. Let's start by doing the derivative d dx of x minus 3 times 2x plus 9. Obviously, the best way to do this would be to expand that out first and then take the derivative. So let's do the derivative of, how about 2x squared minus 6x plus 9x, so plus 3x minus 27, like that. This becomes 4x plus 3. We take the derivative. What we're going to check to see is if that is equal to the derivative of each one of these parts of this thing multiplied together. So let's compare that over here. First of all, the derivative of just x minus 3. This would equal 1. And the derivative of just 2x plus 9, that's just equal to 2. And 1 times 2 equals just 2. So these are not the same thing. What this is proving is that the derivatives do not work this way. You cannot just take the derivative. If you have derivative of two things multiplied together, you cannot just take the derivative of the first and the second and multiply those derivatives. You have to use what's called the product rule, which I'm going to write down right now in this video for the sake of posterity. You do not need to write this down at any moment. The product rule says that we have to do the original function, f of x, times g prime of x, plus the derivative of f of x, f prime, times the original g of x. It's actually a pretty simple rule, but we'll practice that later on when we need to. Right now we don't need to. So, and we're going to finish up with some limit problems, which we should always just do every once in a while. So let's get to it. The first question I'm going to do down here in this space, since I feel like we need to. We're looking for the limit as x approaches 9 of the square root of x minus 3 over x minus 9. The problem, of course, right now is that if we plug in 9 for x, we're going to get 0 over 0. We'll do 3 minus 3 and 9 minus 9. So that's not going to work. What we need to do is get rid of the square root and hope that the problem of x minus 9 kind of cancels out. So we're going to multiply this by the square root of x plus 3 over the square root of x plus 3. It's going to work out and cancel out the x minus 9. I'll show you how. On the top of this fraction, if you were to multiply these two things together, you'll get an x from the 2 square roots of x. You'll have a minus 3 roots of x and a plus 3 roots of x that will cancel out, and you'll have a minus 9. On the bottom of this fraction, you'll have an x minus 9 times the square root of x plus 3. The x minus 9s will cancel out, and so now we have the limit as x approaches 9 of 1 over the square root of x plus 3, which is pretty easy to solve because you can just plug in 9. It's going to be 1 over 3 plus 3, or 1 over 6. And that's the answer to the first question. Question B is actually just a derivative question, honestly. Whenever you see limit as h approaches 0, and you have h on the bottom here, you're about to be asked a question that's I'm basically asking you for the derivative of something. The real question here is, what's the actual function? It looks like what's going on here is we have the square root of, let's see, I would say that I think this is the square root of x, because I see there's your x plus h, your 2 plus h right there. Usually the thing that has h added to it, that's what you want to think about x. The original function here looks like it's the square root of x. And we're looking for what's happening. This is specifically when we're looking for f prime of x when x is equal to 2, which you can further see from the square root of 2 sitting right there. So this is really asking you for, if f of x is the square root of x, what's f prime of 2? That's the question. So the nice thing is, let's go back in time a little bit. F prime of x, when we have x equals square root of x, or x to the 1/2 power, is 1 over 2 roots of x. And that's one that I think the more you deal with it, you get closer to just memorizing it. At this stage, we can just plug in 2. F prime of 2 is going to equal 1 over 2 times the square root of 2, which is, that's it, honestly. That's as far as the answer goes. That would be the solution to that problem. You could rationalize the denominator if you wanted to, but who cares? Question C is got a limit as x approaches infinity, and this means we're talking about end behavior here. So this is less of a math problem and more of a thinking problem. What's going to happen when we plug in infinity into these two x's right there? Well, what's going to happen is that I'll tell you, first of all, is this plus 1 and that 5 minus don't really do anything. We can kind of ignore those. But what we are going to have is we're going to have kind of a we're going to have a 2 times, you might think about it, positive infinity on the top of this fraction. And on the bottom, you're going to have a negative infinity. And since they're both square roots, they have the same degree, so they're growing at the same rate. But what's going to happen here is that there's always going to be a 2 to -1 relationship. So what's going to happen here is that you're going to approach the horizontal asymptote of -2 on that graph. And that's what's going to happen. The negatives actually kind of cancel out there. And then question D, the limit as x approaches infinity of cosine of x, which is a really easy question to answer, does not exist. And the reason why is because if you think about cosine, it just does this forever. Cosine doesn't really do anything definitively as x approaches infinity. As you go further to the right this way, the limit doesn't ever approach one number. It just constantly fluctuates from 1 to -1. So there is no limit for this function. The same thing is true about the sine of x function, so there's also no limit there. Hey, we did it in 25 minutes. That's pretty cool. I'm going to leave this one up to you. I'm not going to do we'll save 139 for a rainy day. But you guys are awesome. Thanks for making it this far in this video. I'm really happy for you to be here, and I will see you in the next one.